Now we're back from the office. We did that integral and we got the result. The result is on the bottom of page 4, or toward the bottom of page 4. The last centered equation is the result, the solution to the heat equation on an infinite domain. And that is u of ys is the convolution integral between g, the initial condition, and that result that we got, or the solution, which we are calling big U. Notice the form that big U has. Is that familiar from any classes you've had before? That is the equation, or the function, for a Gaussian distribution, commonly known as the bell curve. That's interesting, because you would have seen that in a statistics class. And you probably didn't expect to see statistics showing up in this PDEs class. So what's the deal there? It's fascinating, the connection now between probability and statistics and PDEs. There are a lot of connections to be made there, and I love exploiting those connections. So let's look at some of the properties of that function u that we ended up with, because you know that all the information about solving the heat equation is in that function, capital U. The lowercase g was just the given function. So in particular, we're going to look at what we have here. Our solution process basically amounts to we're given a g, and this g is our given initial conditions. And the solution is to take those given initial conditions and do the convolution with u, where u is what we call the heat kernel, or the fundamental transfer function between the given initial condition and the result at any time s. Remember, s is our time variable. And so we can graph a bunch of these capital U's, and we see that they are the bell curves, the Gaussian distributions, and these have various properties. Notice as s gets larger, time plays the role of the standard deviation. The standard deviation, or actually a variance technically. Basically, the standard deviation of this form of the bell curve is 2 times the square root of s. Normally we would see a sigma squared down there if we're thinking of statistics class. And so each of these is a bell curve, some of them flatter than others because some of them have higher s's than others. So as time goes on, the standard deviation is increasing according to 2 times the square root of s. So for low times, this is a very high bell curve, very steep, going down to very narrow tails. And for large times, this is a very wide, fat bell curve with a large standard deviation, but not a lot of height. So notice that because this is a bell curve, that we can apply certain probability and statistics results to this. For instance, as a normal random variable, the integral of a bell curve is 1. If you accumulate the probability of any outcome in a bell curve, the sum of all the probabilities is always 1. And so the integral of u from minus infinity to infinity, the area under any one of these bell curves, is 1. We call that the conservative property, that the area underneath, no matter how small the squash is, it will widen the tails to exactly the extent that the area under every single one of these curves is always 1. And so that's conserved throughout time, s. Notice that this is integrable only when s is positive. So look at this. If s were actually a negative quantity, like if we were to reverse time and make s negative, this would be e to the positive z squared. And that is an integral that blows up. That's an infinite integral. It's only when s is positive, only when time goes forwards, when s is positive, that we can actually integrate this and that it would be a bell curve. So that's a fascinating result with marvelous implications for the physics of heat and diffusion transfer, that it's a one-sided process. Time can only go forwards, cannot be reversed on these processes. The next one is, notice that this is what we call universal, meaning that for the bell curve, because this is an exponential function, there's nothing that we can plug in for z, or s for that matter, that can make u equal to 0. U is positive everywhere. Everywhere. It might be very small, but positive anywhere. And so if we interpret this space dimension z, this variable z, the input to this Gaussian function, remember z equals y minus c. And if you look up at the formula of that convolution integral, I didn't write the formula for the convolution integral up here, but you see that u of y and s depends on adding up or integrating g of xi with respect to xi. And so if we look at the point y equals xi, like if we're looking at how does the contribution of g of y itself contribute to the solution u of y, we would be plugging in 0 for z, and we would get the maximum contribution. So remember, as an integral, that's like adding up all the different areas. Of course, these areas, or these heights, are being multiplied by the g of xi. But if we look at how the weighting of those g of x's would contribute to the solution u of y, we would see that when y equals xi, that contribution is maximum, or that g of xi is being multiplied by the maximum that u could possibly be. And that the farther we get away from y itself, the farther xi travels from y, we get much less contributions because of those tails. So it is universal in that g of xi, wherever xi is, does contribute a little bit, at least, to the solution u of y. But we also see that how those contributions decay. The last property is the smoothing property. Notice that these bell curves are smooth, meaning that they're continuous, but actually all of their derivatives are continuous. No matter how many derivatives we take, we will always have something that is continuous. And that's true then for the solution, no matter what g, no matter what the initial condition is. Consider the case where g might be one of these bell curves itself, but the limiting case where the standard deviation would go to 0. Like, what if s equals 0 had the shape that was infinitely tall, but infinitesimally narrow, meaning this conservative integral that's always 1, what if it were all completely concentrated at one point? You might remember from ODE's class last semester that that's called a Dirac delta function, which is not really a function, it's a generalized function, but it's very useful in applied mathematics. If we take all of the energy and concentrate it as like a spike right in the middle here, then as soon as s is non-zero, we get something that is the bell curve. It might be a very tall bell curve, but it is still a bell curve, meaning that even though that initial condition, the Dirac delta function, is not continuous, it's very not analytical, we would immediately, for any infinitesimally small but positive time, we would immediately have the smooth, perfectly smooth bell curve. So those are all some fascinating properties of solutions to the heat equation that we can see clearly because we've solved for what we call the kernel of the heat equation using the Fourier transform method.